This video continues the topic of semiconductors. Here we'll introduce transistors, specifically bipolar junction transistors, or BJT. Now a BJT transistor comprises two PN junctions. So a PN junction is what a diode is made from. So bipolar junction transistor could look like this, where you have N-type, P-type, and N-type. So you have two PN junctions. And then there are three terminals on a transistor. For a BJT, they're called the base, collector, and emitter. So base, collector, and emitter are the three junctions. And the electrical symbol for this type of transistor looks like this. So we've got the base, collector, and emitter. And we'll denote the voltages at those three terminals. So VB, VC, and VE. For an NPN transistor, electrons are the charge carrier. And so the charge carrier goes from the emitter to the collector, and our convention for current direction is the opposite way of, or the opposite direction of the electron flow. So we show the current going towards the emitter for an NPN transistor. So here's what's referred to as IC, the current through the collector, and then IB is the current through the base. And then here we have VBE, which is the voltage between the base and the emitter, and VCE, the voltage between the collector and the emitter. We've shown here an NPN BJT, but you could also have a PNP. And so in a PNP transistor, then holes would be the charge carrier. NPN is more common. One reason is because electrons are more efficient charge carriers than holes. So the way we can use, or the way that you use a BJT transistor, is that the base current controls the collector current. The most common configuration is called common emitter. So here is a circuit for a common emitter. So we have our voltage supply, and then our load, and then the transistor, and then the emitter is at ground, and so that's why it's a common emitter. And then typically we have a voltage source, VBB, and then this resistor RB determines that, and the voltage source determines the current IB. Here we call this VCC, and then RC. So again we have VBE and VCE, the voltage between the base and the emitter, and VCE, the voltage between the collector and the emitter. And the This transistor, the BJT transistor, has 3 states. We have cutoff, and in the cutoff state, the voltage VBE is less than a threshold voltage, V threshold. Because you see, this right here, this PN junction, is a diode. And so, just as in the diode, an ideal diode, we have voltage and current, and no current flows until we reach the threshold voltage for the diode, and then it acts like a closed switch. So that's for an ideal diode. Well, actually, that's for a real approximation. So this junction here, once it's forward biased, well, before it's forward biased, if the voltage VBE is less than this threshold voltage, then there's no current flowing through, so the collector current is 0. And so that's the cutoff state. And then we have the active state. In that case, VBE is greater than the threshold voltage, and so this junction is forward biased. And in that case, IC is proportional to IB. And here beta is the gain. So typical values of a gain are 100 or 200. So a small current change in IB produces a big current change in IC. And so that's the active region. And then the third state would be the saturation. So here we have where the current through the base, IB, is greater than what's called the saturation current, IB sat. And in this case, IC is equal to its maximum value, IC sat. So I'll show the characteristic curve for a bipolar junction transistor. But first, let me draw a common circuit for it. So if we wanted to just use this in common emitter configuration, we've got the emitter connected to ground. VCC, RC, and here's our voltage between the collector and emitter. And then we have an RB because our signal is VBB. So our input is voltage here, VBB. And then that gives us a V voltage between the base and the emitter, and current through the base, IB. Okay, so in this configuration, we're going to plot VCE versus IC. So here is VCE, and here is IC. So we know something about VCE is that VCE plus the voltage drop across this resistor is equal to VCC. So in the case where VCE is 0, then that means that the voltage drop across this resistor is VCC. And so in that case, IC is equal to VCC over RC, because the voltage drop across this resistor is VCC. And then at the other intersection, we have a case where the current is 0. So if this current IC is 0, then the voltage drop across this resistor is 0. And so we know that VCE is equal to VCC. And so the relationship between the current and the voltage, VCE, is going to be a straight line between those 2 points. Now, to see how this current changes with respect to IB, which is our input, then we plot the collector current as a function of IB, and so that gives us a bunch of different lines. So it looks kind of like and these would be all different values for IB. So with increasing IB, then the collector current increases. Because, so this right here is called a Q point, which is the intersection between this load line and the line for IB. So this is where the transistor is actually going to operate. So if we have a base current of IB2, then we would know that VCE would be this value and the collector current would be this value. And this region to the right of the dashed line I drew is called the active region. So this is active. And so we know that this current is beta times IB. Okay. And that's the case here too. So if we go up to IB3, so this is beta equals IB2, then this IC would be beta times IB3. Now as we increase the base current, then the collector current is going to increase, and so the VCE is going to drop. So as this collector, or as the collector current increases, the voltage drop across here increases, and so VCE drops. And that happens all the way until we get to this line, this vertical dash line, and that's when we get into the saturation state. And the intersection of the load line and that vertical line defines IC, the saturation current. And the saturation voltage, VCE. Now, if you're using a transistor as an amplifier, you'd operate in the active state. And if you just want to use it as a switch, which is what we'll mainly be doing, or what we will be doing, we want it to operate in the saturation state. So over here, in the active region, we have an amplifier. And so a small current is driving a big current. A small current change here makes a big current change in IC. And then in the saturation region, we've reached our IC sat, and so changes in IB over that value don't change IC sat, or don't change the collector current. So let me draw another circuit, or a way that we could use this as a switch. So say we have a microcontroller and we want to control a solenoid. Now the solenoid might operate off of 24 volts and the microcontroller supplies 5 volts. So there's our solenoid. Our bipolar junction transistor, and common emitter configuration. Okay, so we have a solenoid that we want to turn on and off with a microcontroller, say. And the microcontroller doesn't supply enough current, or doesn't have the right voltage to control this solenoid. So we could use a transistor as a switch. And in that case we want it to be in saturation. And so we need to figure out what value for RB we want in order to be sure that the transistor is in saturation. And one thing is missing from this that'll protect the circuit. So we need our flyback diode. Now whenever we open the switch, there won't be a voltage spike that could destroy our transistor. Instead we allow the energy to dissipate in this circuit right here, in the flyback. So the current going through the solenoid is going to be a function of the current going through the base. So this is the collector current, and then this would be the base current. And the base current just depends on our value for Vn, either 5 volts or 3.3 volts, and then the resistor value, Rb. So knowing the gain for the for the transistor, we can determine what value for Rb we need in order to use this as a switch.